Now we are going to talk about the optimization part. So what we are going to talk about basically has nothing to do with overfitting. We only discuss that in optimization. How to make gradient descent better. So why does optimization fail? When you are doing optimization, you will find that as you update with your parameters, your training loss will not decrease anymore. But you are still not satisfied with this loss. Like I just said, you can compare the deep neural network with the linear model, or with the shallow network. You'll find that it did not do better. So you think a deep network doesn't utilize its full power. Thus the optimization obviously has problems. But sometimes, you will even find that your model can't work well at the beginning. No matter how you update your parameters, your loss can't decrease anymore. What happened? A common guess in the past was that because we had reached a place, the differential of the parameter to the loss in this place was 0. When your parameters differentiated to loss were 0, gradient descent had no way to update parameters again. Training stopped at this moment. Your parameters are no longer updated. Of course, the loss would not decrease anymore. Now when the gradient is 0, the first thing that usually comes to people's minds may be a local minimum. So people often say that when doing deep learning with gradient descent, you will get stuck in the local minimum. So gradient descent does not work. Or deep learning doesn't work. But if one day you want to write a paper related to deep learning, you must not say anything like getting stuck in a local minimum. People will think you have no class. Why? Because it's not just local minima that make the gradient 0. There are other possibilities that make the gradient 0. For example, saddle point. In fact, the saddle point means that the gradient is 0. But it's neither a local minimum nor a local maximum. It's like the red dot in this example. It is relatively high in the left and right direction. The front and back direction is relatively low. It's like a saddle shape. So it's called a saddle point. Then its Chinese is called a saddle point. For a place like a saddle point, its gradient is 0. But it is not a local minimum. For the point where the gradient is 0, we call it a critical point. So you can say that your loss has no way to go down. Maybe it's because it's stuck at a critical point. But you can't say it's stuck in the local minimum. Because the saddle point is also the point where the differential is 0. Okay, but today if you find your gradient is really close to 0, it is stuck at a critical point. Can we know whether it is a local minimum or a saddle point? The answer is yes. It is possible to determine where we are on the hypersurface. So why do we want to know whether we are stuck at a local minimum or a saddle point? Because if the model is stuck at a local minimum, our model cannot escape from that point, since everywhere nearby is higher. You are currently at a position which is the point with lowest loss nearby. So the loss will be higher no matter which direction you go. Thus the model doesn't know where to go for the next step. However, if you are at a saddle point, then it is all right. If you are at a saddle point, there remain some directions you can go towards. Which means it is still possible to make the loss lower, as long as you are able to escape from the saddle point. You may be able to improve your model's loss. So, it is worth investigating whether a critical point is a local minimum or a saddle point. So how do you determine whether a critical point is a local minimum or a saddle point? We are going to use a little bit of math here. But don't be afraid, the math here is not very hard. It is just simple calculus and linear algebra. If you failed to understand this part, you can just skip it. This part has nothing to do with the contents later on. Okay. So again, how do you determine whether a critical point is a local minimum or a saddle point? To answer this, you need to know the hypersurface shape of the loss function. But how do we figure out how the loss function looks like? The network itself is very complicated. The loss function, which is calculated from the network, is also very complicated. Then, how do we find out the shape of our loss function? Although it is hard for us to find out the entire shape of the loss function, if a certain set of parameters is given, for example, the blue theta prime here, we are able to explicitly write out the loss function near theta prime. Its form is like this. So the complete formula of L of theta can't be written out explicitly. But if we restrict ourselves to the neighborhood of theta prime, you can use this formula to approximate it. You may ask, what is this? There are so many colors in this formula. What is this? This is the Taylor series approximation. I assume you have learned this already in calculus, so I won't go into the details of this formula. But maybe I can give you a brief picture of it. In this formula, the first term is L of theta prime. This term indicates that when theta is very close to theta prime, L of theta will approximate L of theta prime. What's the second term? The second term is the transpose of theta minus theta prime multiplied by g. What is g? G is a vector. The gradient vector. We talked about gradient last week. We'll use a green g to represent the gradient, which is a vector. So, what information can the gradient give us? This gradient will make up for the gap between theta prime and theta. Although we said that theta and theta prime should be close, there are still some gaps between them. This gap, for the first term, we use the gradient to represent the gap between them. Okay, how about g? Gradient will sometimes be written as the gradient of L of theta prime. G is a vector. Its ith component is the derivative of L with respect to ith component of theta. By only considering g, we cannot fully describe L of theta. You have to look at the third term. What is the third term? The third term is related to Hessian. There is an H here. H is called Hessian. It is a matrix. This third term is the transpose of theta minus theta prime multiplied by H, multiplied by theta minus theta prime. So the third term will make up for the gap between the real L of theta, after adding the gradient. What is inside this H? This H consists of the second derivative of L. What is the value of the ith row the jth column? The value of the ith row the jth column is the derivative of L with respect to the ith component of theta. Then put the derivative of L with respect to the jth component of theta. Then put the derivative of L with respect to the ith component of theta. The result of the secondary derivative is this Hij. If you don't understand well here, it doesn't matter. Anyway, you just remember this L of theta. This loss function, this error surface near theta prime, can be written like this. This formula is related to two things. It has something to do with gradient. It has something to do with Hessian. Gradient is first-order differential. Hessian contains second-order differential. If we move to one critical point, what does that mean? It means the gradient is zero. That is, the green term is completely gone. G is a zero vector. The green term is completely gone. Only the red one is left. So at the critical point, this loss function can be approximated as L of theta prime plus the red term. We can have a picture of the error surface near theta prime based on the red term. Knowing what the error surface looks like, I can judge if theta prime is a local minimum, or a local maximum, or a saddle point. We can rely on this to understand the topography of this error surface. Approximately. Knowing what its topography looks like, we can know that what state it is in now. This is Hessian. Then let's take a look at that according to Hessian. According to this red term. How to know the shape of the error surface near theta prime. For convenience, we use the vector v to represent theta minus theta prime. Theta is a vector and theta prime is also a vector. We use the vector v to represent the result of theta minus theta prime for any possible vector v. The value of its transpose multiplied by h in itself is always greater than 0. In other words, no matter what the value of theta is, V is possible to be any vector. It means that theta minus theta prime can be any value. And theta can be any value too. No matter what the value of theta is. The value in this red box is always greater than 0. What does it mean? It means that the value in the red box is always greater than 0. Which also means that L of theta is greater than L of theta prime. Regardless of the value of theta, as long as it is near theta prime. L of theta is always greater than L of theta prime. What does it mean? It means that L of theta prime is the lowest point around it. So it is a local minimum. On the other hand, for all possible V, if the value of its transpose multiplied by H in itself is less than 0, then that is, the value in this red box is always less than 0. In other words, no matter what the value of theta is, the value inside the red box is always less than 0. What does it mean? It means that all the possible values in this red box are less than 0. It means that L of theta prime is always greater than L of theta. If L of theta is always less than L of theta prime, then it means that L of theta prime is the highest point around it. So it is a local maximum. Suppose there is a third situation that the value of V transpose multiplied by H and V is sometimes greater than 0 and sometimes less than 0. With a different V and a different theta. The value in the red box is sometimes greater than 0. And sometimes less than 0. It means that around theta prime. Sometimes L of theta is greater than L of theta prime and sometimes L of theta is less than L of theta prime. Around L of theta prime, there are some high regions and some low regions. What does it mean? This means that it is a saddle point. But there is still a problem. With the red term, we can now know that whether it is a local minimum, a saddle point, or a local maximum. But in this case, we have to substitute all the possible value for V. And check that the value of V transpose multiplied by H in itself is greater than 0. Or less than 0. How can we check the results of all possible V? So there is an easier way to check which condition will happen. We will tell you the conclusion directly. It has been taught in linear algebra. If for all possible V, the results of V transpose multiplied by H and V are all greater than 0, then this kind of matrix is called positive definite. What are the properties of a positive definite matrix? All its eigenvalues are positive. So if you have calculated the Hessian, you don't need to multiply it by all possible V. You just have to take a look at the eigenvalues of this H. If you find that all its eigenvalues are positive, it means that this condition is always true. The result of V transpose multiplied by H and V will be greater than 0. Which also means it is a local minimum. So, you can see, from the Hessian matrix, whether it is a local minimum. You only need to calculate the Hessian matrix. If its eigenvalues are positive, then it is a local minimum. That's it. Vice versa. If, in this situation, for all V, V transpose multiplied by H and then multiplied by V is less than 0, then H is negative definite. Which means that all eigenvalues are negative. If all eigenvalues are negative, it ensures that it must be a local maximum. If the eigenvalues are sometimes positive and sometimes negative, it means it's a saddle point. Supposing you don't understand it well, you can remember the conclusion that all you need is to figure out what the Hessian is. It is a matrix. If its eigenvalues are all positive, it means that we now reach a local minimum. If they are sometimes positive and sometimes negative, it means we now reach the saddle points. As we mentioned, we can judge whether it is a local minimum or a saddle point. If, as what we just talked, you don't understand it well, there is an example. We now have the most useless network ever. How useless is it? We first enter an X, which only comes with one new row multiplied by W1. Furthermore, this new row doesn't come with a vectorization function. So, the output is merely X multiplied by W1, and then multiplied by W2. This output is called Y. Anyway, this function is very simple. Y is equal to W1 times W2 times X. This is the most useless neural network ever. We also have the most useless training data set ever. This data set includes only one record. When it is X is equal to 1. Its level is 1. So, if we put 1 into it, you hope the final output to be as close to 1 as possible. The most useless training ever. Then, the most useless training ever. Its error surface is able to be showed directly. Anyway, there are only two parameters, W1 and W2. And there is no bias. Assuming there is no bias. And there are only two parameters, W1 and W2. This network has only two parameters, W1 and W2. We can exhaust all the values of possible W1 and W2 to derive the loss of each combination. Then, we can draw the error surface like this. So, here is high. The loss here is high. The loss here is also high. The losses are high in the four corners. Okay. Then, with this picture, you can see that there are some critical points. Where are those critical points? At this black spot 0, 0. The origin point is the critical point. Then, in fact, there are also a row of critical points next to this line. A row of critical points are next to this line. If you go further to analyze whether they are saddle points or local minima at the center of the circle, you will find that it is a saddle point at the original point. Why is it a saddle point? If you go in this direction, the loss will increase. Go in this direction, the loss also increases. Go in this direction, the loss decreases. Go in this direction, the loss decreases. It is a saddle point. And these two groups of critical points, they are all local minima. So in this valley, there is a row of local minima. There is another row of local minima in this valley. And at the origin, there is a saddle point. This is the conclusion we get by brute force searching the error surface. We brute force search all the parameters, calculate the loss with the loss function, and draw the error surface to get this conclusion. Now suppose we don't use brute force search. How can we tell if a point is local minimum or a saddle point? Well, we can write out the loss function. This loss function, denoted L, is y hat, the correct answer, minus the model's output, which is W1 times W2 times X. We take square error here. There is only one data. So we won't have to sum over all training data, because there is only one piece of data anyway. Plug in X equals 1 and Y hat equals 1. I have said that having only one training data is pretty lame. So since there is only one training data, the loss function is 1 minus W1 W2 squared. Then you can solve for the gradient of this loss function. We won't talk about the details here. If you still remember calculus, do the math and you will know that this is correct. The partial derivative of L with respect to W1 looks like this. The partial derivative of L with respect to W2 looks like this. We call this thing G, the so-called gradient. When will the gradient be 0? When will it reach a critical point? For example, if W1 equals 0 and W2 equals 0. At the center of the circle, if you plug in 0 as W1 and W2, the gradient will be 0. If you plug in 0 as W1 and W2, both partial derivatives of L will be 0. Then we can know that the origin is a critical point. We now know it is a critical point. But is it a local maximum? Is it a local maximum, local minimum, or a saddle point? You will have to look at Hessian to answer this. It depends on the Hessian matrix. Of course, we have already brute force searched all possible W1 and W2, so you already know that it is obviously a saddle point. But suppose we haven't searched for all the possible losses, so we have to see if we can use H. Use Hessian to see which critical point it is. How to calculate this H? H is a matrix. This matrix collects second derivative of L. So the element located in the first row and the first column in this matrix means that W1 should differentiate L twice. The element located in the first row and the second column is to differentiate L with W2 first. Then use W1 to differentiate L. Here is W1 to differentiate L. And W2 to differentiates L. Lastly, W2 should differentiate L twice. Combine these four values. Is R Hessian? What is the value of this Hessian? Here I have shown the formula of Hessian. You just need to substitute W1 for 0 and W2 for 0. After that, at the origin you will obtain Hessian, which is a matrix like 0, -2, -2, 0. Okay, this matrix tells us. This Hessian can tell us whether it is a local minimum or a saddle point. To do so, you have to look at the eigenvalue of this matrix. Calculate and find that there are two eigenvalues for this matrix. 2 and -2, one of which is positive and the other is negative. It means that it's a saddle point. We just mentioned that one positive eigenvalue with a negative one should be a saddle point. Okay, so let's take an example to show that how can we use Hessian to distinguish between the saddle point and the local minima when we come across a crucial point. If you stuck in the saddle point today, maybe you don't need to be worried about that. Why? Because if you find out the reason to make you stop is because of the saddle point, there may be a chance to heave a sign of relief. Why? Because H can not only help us to judge whether it is a saddle point or not, but it also points out the possible update direction of the parameters. In the past, we always update the parameters with the gradient, g. However, sometimes we go somewhere and found that g becomes to 0 and can't use it anymore. G disappears, gradient disappears. But if it's a saddle point, you can still use H. How to use H? How can H tell us how to update parameters? Let us assume that U is the eigenvector of H, and lambda is the eigenvalue of U. That is, H has an eigenvalue called lambda, and its corresponding eigenvector is called U. Here if we replace V with U, what will happen? If we multiply U by H on the left side and on the right of H respectively, that is, U transpose multiplied by H and multiplied by U, what will we get? H multiplied by U will get lambda U. Why? Because U is an eigenvector. So H multiplied by an eigenvector will get lambda eigenvalue multiplied by an eigenvector. So here we will get U transpose multiplied by lambda U. Then tidy up. Multiply U transpose with U can get the square norm of U. Finally, we get lambda multiplied by the square norm of U. So for this term, suppose V is an eigenvector. If theta minus theta prime is an eigenvector, you will find that this red term is actually lambda U norm square. What will happen if the eigenvalue lambda is less than 0? If the eigenvalue is less than 0, the term lambda U norm square will be less than 0. Because U norm square must be positive, the eigenvalue is negative. Then this term will be negative. That is, the transpose of U multiplied by H and U is negative. That is, the term in this red box is less than 0. Assuming that theta minus theta prime is equal to U, then this term is negative. That is, L of theta will be less than L of theta prime. In other words, suppose theta minus theta prime is equal to U. That is, theta is equal to theta prime plus U. Adding U to the original parameter of theta prime updates the parameters along the direction of U and gets theta. You can make the loss lower according to this formula. If theta minus theta prime is equal to U, the loss will decrease. So the only thing you need to do is to make theta equals to theta prime plus U. Then the loss will decrease. You only need to update the parameters along the direction of U, or the direction of the eigenvector. And then you can make the loss lower. Although there is no gradient at the critical point, we don't need to panic. If we are at a saddle point, You just need to find the negative eigenvalue. Then find out its corresponding eigenvector. Add theta prime with this eigenvector. Then you can find a new point, with a loss lower than the original point. In case you are not totally clear, let's take a look at a real example. We have just discovered that the origin is a critical point. Its Hessian looks like this. Then I found out that the Hessian has a negative eigenvalue. This eigenvalue is equal to -2. This eigenvalue is equal to -2. What does the corresponding eigenvector look like? Well, there are many. In fact, there are infinitely many corresponding eigenvectors. Take one for example. 1, 1 is its corresponding eigenvector. Then we only need to follow the direction of u. Follow the direction of the vector 1, 1, 2. Update our parameters. Then you can find a point with a loss lower than the saddle point. In this example, the saddle point is at 0, 0. You will have no gradient at this point, so the gradient won't tell you how you should update the parameters. However, the eigenvector of Hessian tells us to update in the direction of 1, 1. Then you can make the loss smaller. Just update along the direction of the eigenvector u, which is 1, 1. You can make your loss lower. That means you can escape from the saddle point, and then make your loss lower. So from this perspective, the saddle point seems to become less frightening. When you're training a model, your gradient becomes 0. And the training process stops. If it stops because of a saddle point, there seems to be hope for it. But of course, Hessian is seldom computed in the actual implementation. But why? The second-order partial derivatives need to be calculated for the Hessian, so it involves a huge amount of computation. Not to mention you have to find out its eigenvalues and eigenvectors. Thus in practice, this method is hardly used to escape from saddle points. Next, we will talk about the other ways to escape from saddle points. All of them require much less computation than the Hessian. The reason we introduced this saddle point and the eigenvectors of the Hessian is because I'd like to tell you that you don't have to be too worried. Even if it got stuck at a saddle point, you can resort to it in the worst case. Well, here comes the question. The question is whether saddle points or local minima occur more constantly during training. As shown earlier, saddle points are not that scary. And it would be very nice if we encounter them more often than local minima. Which of them is more commonly seen? After all, here I am going to tell an irrelevant story. Let's get started. It was around the 16th century. More concisely in 1543. The story took place. Constantinople fell that year. Here is a painting depicting the fall of Constantinople. Constantinople, originally the capital of the Eastern Roman Empire, was captured by the Ottoman Empire, and so the Eastern Roman Empire collapsed. During the siege of Constantinople by the Turks, the emperor of the Eastern Roman Empire, Constantine XI, was desperate for counterattacks against them. And he was counseled to seek help from a magician called Diarena. By the way, this is a true story, you know. From the three-body problem. Then, who is Diarena? She has the same ability as Zhang Fei, who was able to decapitate the enemy commander by himself, despite being outnumbered. So did she. She could chop off the Sultan's head directly, without being noticed by anyone. Everyone was wondering why she could do so. Did she really have magical power? So they made her exhibit her power. At that time she took out a holy grail, which baffled everyone. Why were they so surprised after having seen the holy grail? Because this holy grail was originally placed in the basement of Hagia Sophia. And it was placed in a sarcophagus. This sarcophagus was sealed. No one can open it. But Diarena got the holy grail from it, and put a bunch of grapes in it. Constantine XI wanted to verify whether Diarena had this ability. He brought some people to pry open this sarcophagus. And he found that the Holy Grail was taken away. There was a bunch of fresh grapes in it. He knew that Diarina had the ability to take the head of the enemy admiral. Why could Diarina do these things? The sarcophagus was closed from your perspective. You are looking at it from a three-dimensional space. From the perspective of three-dimensional space, the sarcophagus was closed. There was no way to get into it. But Diarina could enter the four-dimensional space. From the high-dimensional space, there was a way to enter this sarcophagus. It was not closed. As for whether Diarina succeeded in assassinating the Sultan, you can imagine that he failed. That's why Constantinople fell to the enemy occupation. Why did he fail? Please watch Death's End by yourself. Anyway, from a three-dimensional perspective, there is no way to go. There is a way to go in a high-dimensional space. Is the error surface the same? In a one-dimensional space, one-dimensional error surface with one parameter, you will feel as if there are local minima everywhere. But is it possible that when be viewed in a two-dimensional space, it's just a saddle point? People often draw pictures like this to tell you that the training of deep learning is very complicated. If we move certain two parameters, the error surface changes are very complicated. It looks like this. Obviously, it has a lot of local minima. I have a local minimum now. But is it possible that this local minimum just looks like a local minimum in a two-dimensional space? In a higher dimensional space, it looks like a saddle point. In a two-dimensional space, we have no way to go. Will there be a way in a higher dimension? For a higher dimension, we can't visualize it. We can't really show it. Will there be a way to go in a higher dimension? If the dimension is higher, are there more ways to go? So, when we are training a network, the number of parameters is often more than 1 million or tens of millions. So our error surface is actually in a very high dimension. Right? The number of parameters represents the dimension of our error surface. The parameter is 10 million, which means the dimension of the error surface is 10 million. The dimension is so high. Will there actually be so many ways to go? Since there are so many ways to go, will there be few local minima at all? In fact, if you do some experiments yourself, you'll find this hypothesis to be correct in general. This graph represents the result of training a certain network. Each point represents the Hessian of a network after it has gone through training. So, every point here represents a network. In short, we train a network until its gradient decreases to the point that it is stuck on the critical point. We then analyze that particular set of parameters and see whether it is a saddle point or a local minimum. What about the vertical and horizontal axes? The vertical axis represents the loss during training. To be more precise, it represents the minimum loss we can achieve during the training process. More often than not, the loss can't be lowered anymore even if it is still high, since it is stuck at the critical point. In some cases, the loss can be reduced a lot before getting stuck at the critical point. We have explained the vertical axis. What about the horizontal axis? The horizontal axis represents the minimum ratio. What does the minimum ratio mean? The minimum ratio is the number of positive eigenvalues divided by the number of all eigenvalues. So, if all eigenvalues are positive, it means the critical point is a local minimum. If both positive and negative eigenvalues exist, it means it is a saddle point. In practice, it is almost impossible to find a critical point with only positive eigenvalues and no negative eigenvalues. In our example, the minimum ratio, whose definition we have just defined, is around 0.5 to 0.6 at most. It means that only half of the eigenvalues are positive, while the other half are negative. So, even if it means the further to the right we go on this graph, the more the critical point looks like a local minimum. None of the critical points is truly a local minimum. Even in the most extreme cases, negative eigenvalues still account for almost 50% of eigenvalues, while the other 50% are positive eigenvalues. This means that in all dimensions, half of the directions would increase the loss, while the other half would decrease the loss. Judging from experience, local minima aren't actually that common. More often than not, during the training process, the gradient becomes too small, and the parameters stop updating, because we are stuck on a saddle point. Now, we're going to talk about whether there are any possible solutions when we're stuck on the critical point. Like I just said, even if the occurrence of local minima may not be that common, being stuck on a saddle point, or somewhere near a saddle point that is also flat, could still make the gradient too small and stop the parameters from updating. Let's pause for a bit and see if any of you have questions to ask.